types of biasing. So a revision of types of biasing. So just we will take a glance of this types of biasing. So now we have 5 methods to bias your circuit. Out of this 5 methods, so nothing but biasing is nothing but additional voltages or additional circuitry which can give you quiescent values or operating voltages. So now here, based on the circuitry what you connected, we have 5 methods of biasing. First one is your fixed biasing. So in this fixed biasing circuit, so we are connected one VCC with a large amount of resistance which we have treated it as a RB. So base resistance of RB, so this base resistance RB which you are connected to the base of your transistor must be very high. So then this VCC is applied through this RB. So where in an NPN transistor base is P type, hence we applied, you know, to apply the base to emitter junction forward, we applied the positive VCC through your resistor RB. Then the IB is flowing through this base terminal, base current IB is flowing. Thereafter, so it is in common emitter configuration, your collector current is equal to beta times of your IB, where that beta is your current gain of the CE amplifier. Right now, so in order to analyze this fixed bias circuit, is it a good biasing technique or will it give the poor response at the output? That we have to determine. Actually, it's a simple to construct. So your circuit in a fixed biasing method, it is very simple to construct. We have used like your VCC we connected to the collector. Instead of that, we also included one more resistor RB and we connected through VCC. Hence, the simplest way of biasing is your fixed bias. But the thing is here, the disadvantage is it is having very poor stability. So out of 5 methods, this fixed bias circuitry will have the poor stability. So the stability factor is very high. So we prefer the stability factor value which will be very less. So the lower values having the more stability, the higher values of stability factor leads to the poor stability of a amplifier. Hence, so here fixed bias circuit is not preferable, but wherever you require the easiest way of construction, so then you could prefer this fixed biasing circuit, right? So now coming to your analyzation part, so we have to determine why it is having the poor stability, so that we have to learn now. So now in order to learn that, so already I have mentioned in an amplifier, in a configuration while you are taking your DC characteristics, we have not at all connected any capacitor, but whereas here in order to function a transistor as an amplifier, we are superimposing the weakest AC input signal on that operating voltages. That operating voltages can amplify the weakest input signals to the required level at the output. Hence here we have used your coupling capacitors. These coupling capacitors are utilized to couple your input, the AC input signal, and the function of this coupling capacitor C1 will block the DC, the additional DC which comes from your input signal, whereas the C2 is connected at the output terminal. So out of the two coupling capacitors, one is connected at the input, the other one is connected at the output. So now this C2 is connected at the output terminal. So in order to take the output, or take your output across the load resistor RL, we are taking the output across your collector terminal or across your load resistor RL. So we connected one more capacitor, and this capacitor can block the DC signal which is present in the output. So the additional DC signal which is present in the output will be blocked by this coupling capacitor, and a pure AC signal or with a zero reference level, your signal output will vary Vm, and with a minimum level of your minus Vm. So with that we will get the total amount of voltages are 2 Vm signal at the output with a zero reference axis. So in order to block the DC signals which is presented at the output, so we have coupled your C2. Now while you're doing your DC analysis, the DC signals are having the frequency of 0, hence here the reactance offered by the capacitor is Xc is equal to 1 by 2 pi Fc, where F is 0. So reactance offered by the each capacitor is infinite. Hence, so that infinite reactance if a capacitor is offering, so that can be replaced with the open circuit. Hence, we have open circuited your C1 and C2. Now, in order to use your transistor as an amplifier, we have to couple the C1, C2. But to analyze your DC signals, we have to make that AC input signal to 0, as well as we have to open circuit, or sorry, we have to replace this C1 and C2 with a open circuit. Since your reactance offered by the capacitor with the applied DC signal is infinite, hence these are replaced with open circuit. Now, so a direct connection we have from VCC to VCC through your RB is connected to base, and through this VCC base to collector junction, output junction is reverse bias through your resistor RC, and it is connected coupled to the collector terminal. So plus VCC we are connecting. So plus or a positive DC signal we are connecting to the collector terminal. So collector terminal is of N type, hence the output junction become reverse bias. So your transistor is operated under linear region. Now with this applied VCC, RB and RC, we are making a input current to be transferred through the base region, as well as we will collect the output collector current, which is IC. Now next one. So second step is, so in order to analyze this, so we are taking one will be the input loop, the other one will just we are just dividing into two loops. One loop will be the input loop, the second one will be the output loop. So this total circuit is divided into two loops. One will be the input, the other one will be your output loop, or be base to emitter junction loop and collector to emitter, because emitter I am taking it as a common terminal, hence it is CE loop. Now, so now we have to analyze. So what is the base current and what is the amount of collector current? So that collector quiescent values we have to maintain a constant value. This should not depend on either of beta or either of your temperature or either of your reverse saturation current under reverse bias junction voltages. So now, so here we are applying the KVL in the input loop. When I apply a KVL in the input loop, the amount of base current is equal to VCC minus of VBE. So VCC minus of drop across here the resistor RB, IB into RB, minus of VB, like that also you can write, but I am taking it as a plus minus VCC here, and hence here plus of IB RB plus VB is equal to 0. So from this first equation we got here the base current IB is equal to VCC minus VB divided by RB. Now amount of base to emitter junction voltage always decreases with an amount of minus 2.5 millivolt per 1 degree centigrade rise in the temperature. So base current now in a fixed bias current, now it is base current is equal to VCC minus VB, where VCC voltage it should not, where RB is your resistor RB, which is IB is the base to emitter junction out. So if my temperature, the room temperature is increasing, when the room temperature is increasing, the amount of base to emitter junction voltage will decay with a magnitude of 2.5 millivolt for every degree centigrade rise in temperature. So now the base current is directly, now it is dependent on VBE. Hence, output collector current, what is our output collector current in common emitter configuration, is equal to IC is equal to beta times of your IB. So, IB depends on VBE as well as it also depends on your beta. So, this beta is also so it is temperature dependent, and IB is also temperature dependent due to the VBE. Hence now, so this is having a poor stability due to this reason, because the base current as well as your collector currents depends on your temperature. Now, so next we will move to your output loop of your CE configuration or CE amplifier. So in the second loop of your CE configuration, so here we have the KVL. When you apply a KVL at the output loop, then we have minus VCC plus drop across your collector resistor RC minus of VCE or plus of VCE. So minus I have taken here minus VCC, so plus ICRC plus of VCE, where collector emitter voltage is the quiescent voltage. So operating voltage, in order to find that, we have to take VCC minus of ICRC, where IC is equal to, we replace this IC with the beta IB, then sorry, IC is, as we know that IC is equal to, in a common emitter amplifier, beta IB. Hence here IC is equal to beta DC, as we know that our base current is equal to VCC minus of VBE divided by RB. Whereas here the amount of collector current which is passing through the collector terminal of transistor is not dependent on the load resistor or the collector resistor which you connected on at C. Whereas here the beta, VCC and VBE are the constant are constant for a transistor, and IC depends on RB. So choose the value of your RB to get a constant VCC. Is it clear, everybody? Everyone, is it clear, Nana? Tell me, Ma. Is it clear, everyone? Do you have any doubts, Nana, regarding that fixed balancing circuit? Do you have any doubts? Okay, right. Now I'll move to your next slide. Is it clear, the concept of fixed balancing? So the quiescent values of your fixed balancing circuit depends on the temperature sensitive parameters, which are your beta DC as well as your base to emitter junction voltages, hence which gives you a poor stability. Hence we'll move to your next balancing technique, which is your voltage divider balancing. Now, these are the some of the disadvantages of your fixed bias circuit. Whereas coming to your advantages, this circuit is very simple to construct and which uses a very few components. So the operating point can be fixed at anywhere in the active region by simply changing the values of RB, thus which provides your maximum flexibility in the design. So only for the design part of your biasing circuits. So it is very flexible to use your fixed bias circuit. Coming to your disadvantages, now it is unstable because of it is too dependent on your beta as well as on the base to emitter junction voltages. So the improper bias stability can lead your the shift in the DC operating point. So hence, so in order to avoid that shift in the or to compensate the shifting the DC operating point, we have to add one resistor at the emitter. So that emitter voltage, so the voltage drop across your emitter can compensate the base current increase or it can increase or decrease. So it can control your that increment of your base current due to your VBE and and the temperature dependence of your beta so can be reduced using your emitter resistor or the emitter voltage drop across your emitter resistor. So like this we can compensate the fixed bias circuit disadvantages. Next I'll move to your next slide, which is your voltage divider biasing technique. Now this voltage divider biasing technique, so simple here also this is very simple construction. Now instead of connecting your resistor only one single resistor RB to a VCC to the base, we use the potential divider network R1 and R2 which is connected from your VCC to the base of your transistor, and emitter is actually we are grounding in your fixed bias, so without any emitter resistor. Instead of that, what we are doing is we have provided one emitter resistor RE and the other end of your RE is connected to the ground. So now, so amount of voltage which you are applying to this transistor is, if I treat it as a VB, then this VB is equal to base voltage is equal to base to emitter junction voltage plus of the emitter voltage. So that base to emitter junction voltage depends on the amount of input what you apply on the external AC input, and this VE is dependent on the resistor, the amount of current flow through your resistor RE. Hence it is equal to IE into of RE, where IE is equal to IB plus of IC into IB plus of IC into RE. So now in order to analyze this voltage divider biasing circuit, we are following the same methodology like your fixed biasing circuit, but the complexity of your circuit is quite it is high compared to your fixed bias circuit. Hence, so we are moving to the Thevenin equivalent. We are using your Thevenin theorem, and using the Thevenin theorem, we are going to replace the input circuit with the equivalent Thevenin voltage in series with a Thevenin resistance. So now, so like your fixed bias, so we also here mentioning the two loops. One loop, the first loop will be a base to emitter junction loop, and the second one will be the collector to emitter junction or collector to base junction output loop, right? So now the advantage are which provides your high stability in your using your voltage divider biasing circuit. So we would have a high stability compared to the all the remaining techniques, and this biasing circuit will provide your the quiescent values which almost they are independent of your current gain or the beta factor, as well as is also independent of the temperature raise due to the compensative methods which you are going to utilize in your voltage divider biasing technique. Hence, so the advantages, these are the some of the advantages of your voltage divider biasing network. Now coming to the analysis part. So now this input loop, so we have just replaced like your fixed bias, so we have replaced the coupling capacitor and we have made that we are doing a DC analysis, hence the AC signal, AC input signal must be 0. So we just open circuited that AC input signal. Thereafter we just open circuited your capacitor, since we are doing a DC analysis. DC analysis, the reactance is very high, so those are replaced with open circuit. Now R1, R2. Now this RTH is the parallel combination of R1 and R2, where VTH is the voltage across your base terminal. So the voltage across the base terminal is nothing but the amount of current flow through your voltage divider network. Let I treat it as a I is equal to, or I1 is equal to, now it is equal to VCC divided by R1 plus of R2, R1 plus R2, where the amount of voltage at base is VTH, which is equal to, so I into R2, where I1 into R2. So I1, if I replace with VCC by R1 plus R2, then VThevenin is equal to R2 by R1 plus R2 into VCC. So now we will replace this input loop, this total input circuit components with this voltage divider network with a single voltage source in series with a single resistance, input resistance R Thevenin. Hence, if we apply the KVL in the input loop, then it is easier to calculate your base current IB. So why we are replacing this total circuit into a single voltage source V Thevenin and R Thevenin is, so to find here the base current or the input current, so we have to replace this total circuit into a single voltage source with a single resistance RTH. So in order to simplify the calculation of your base current, we replace this circuitry with a Thevenin equivalent circuit. Right. Next, we'll move to your next slide. So in this next slide, so the equivalent circuit at the input loop, and this is your equivalent circuit at the output loop. Next, we'll move to your applying your KVL to find your base current. So in order to find your base current, now we have taken here minus VTH plus of IB, the amount of current through your RTH is base current, IB into RTH plus of VBE plus of amount of voltage drop across your resistor RE is IE into the amount of current flowing through your resistor RE, emitter terminal is IE into RE. So now what is IE is actually is equal to IB plus of IC. So in a common emitter amplifier circuit, IE is equal to IB plus of IC. Now we know that IC is beta times of IB, hence here your emitter current is equal to, now I replace IC with beta IB, then it is equal to IE in terms of IB is equal to beta plus 1 time of your IB. So now, so if I replace, so I wanted to find, so the base current or the input current, hence we are replacing IE with beta plus 1 times of your IB. So substitute IE value in the above equation, we will get the equation for the base current IB is equal to VTH minus of VBE divided by RTH plus of beta plus 1 plus into R. Now, so this is your base current in your voltage divider network. Next, we'll find here what is the amount of collector current. So now in order to find that, let I am taking a common emitter output loop, CE loop. So when I am taking the CE loop, then it is equal to KVL I am applying at the output loop, minus VCC drop across your RC. So minus of VCE minus of I, the drop across here resistor RE. So now I am taking this as a, so minus VCC plus ICRC plus of VCE plus IE into RE. As IE is beta plus 1 times of your IB. So beta plus 1, let I approximate with a beta. So IE is equal to, I'll write here. So IE is equal to beta plus 1 times of IB. So beta plus 1, let I just ignore the 1. So then it is equal to IE is beta times of your IB. So where beta IB is equal to IC. Hence, IE is approximately equal to, emitter current is approximately equal to IC. So now if I replace this with the IC value, then we have here IE with the IC value, then we have IC into of RC plus of RE. So from this we'll get the output current, which is equal to IC is equal to VCC minus of VCE divided by RC plus RE. RC plus of RE. Now just verify your collector current. Now this collector current doesn't depend on the beta. Now it is doesn't depend on your beta value. It depends on the collector resistor RC as well as on the emitter resistor RE and the fixed magnitude of your DC voltage, which is VCC. Hence, so in your temperature dependent factor of beta, so like your fixed biasing where the collector current is dependent on the beta is almost, it is here depends on only on the resistor, the components which you connected in the circuit, voltage divider biasing circuit. So these are the fixed values. So hence we can maintain the collector current which is constant, or the operating current which is constant and that doesn't vary based on the temperature increase or decrease. So this is about your actual voltage divider biasing advantages. Now, do you have any doubts regarding that voltage divider biasing network? Then I will move to your next PPT, which is stability. Yes. Is the chat box is available to everyone? Please answer, Nana. Is the chat box is available to everyone? Do you have any doubts regarding your biasing techniques? Is that clear? The concept is clear, right? Do you have any doubts? Will I move to your next concept, which is stability? Okay, right. I'll move to the next concept, which is stability. Let me learn about the stability, thermal runaway, and so what are the bias compensation techniques. Now, so let me move to your what does mean by a need for a biasing. Already I will explain you. So in order to put your quiescent point at exactly at the DC load line center, so we are adding your DC voltages and an additional circuitry which can maintain the DC bias voltages and currents. So our input will be superimposed, hence we'll get the distortionless output signal, and those weakest input signal what you apply on the base of your transistor will be amplified to the required level using this DC voltages. Alright, that amplification is done with the applied DC additional DC biasing circuit. Now, so almost your transistor must be operated under linear region. So in addition with that linear region, so we should also maintain the quiescent point exactly at the center. Hence, we are providing the biasing networks, right? So now, if I have moved my operating point for any changes in the DC signals, these are the outputs, the distorted outputs at your positive peaks as well as at the negative peaks due to your shifting of the DC load line. Now, so need for stabilization is so main criteria for stabilization is, so we have to maintain the output should not vary based on the three variations of the parameters. So first one, the parameter which can change your stability will be temperature. Next, the second one, the individual variation. The third one will be the thermal runaway. So due to these three factors, we require the stabilization. So we require the stabilization due to these three factors. So where the collector current is temperature dependent. So due to that, you can have the shifting in the quiescent points. So due to that, we have the distorted output. Next, if I change any parameters, like if I change my transistor, same type of transistor if I am taking, so I am taking a same type of transistor, just I replace the existing transistor with a new one, so the same characteristic, and we know that no two devices having the similar characteristics. So due to that, so the operating point may shift from the existing point from the center. So with that we can get your distorted output. So that also we have to stabilize. Next, thermal runaway. So due to this improper biasing, so improper biasing circuitry, so it will be self-destructed. Your transistor must be self-destructed. So with that, so we can get your distorted output due to your self-destruction of your transistor. So due to the increase in the temperature. So that is known as the thermal runaway. Now next thing is in order to find, so how this collector current dependent on the temperature. As we know that in a common emitter configuration, the collector current is equal to beta IB plus of ICEO. Actually, will give the equation which is beta times of IB only, and we'll neglect that ICEO. What is ICO is the reverse saturation current due to the output junction reverse bias. Now, in a transistor, when it is operated under active region, so your output junction is reverse bias. So when the output junction is reverse bias, the minority, the drift of your minority charge carriers into your collector region, we have some additional current which is in the range of microamps. So that is ICEO. ICEO is calculated in a common emitter configuration with the input terminal open circuited. Now input terminal open circuited means your input junction is your base terminal is open circuited. So the forward bias of your PN junction diode base to emitter junction is we are just open circuited your base. Then the amount of current due to your base to collector junction reverse bias is known as ICEO, that is reverse saturation current or the leakage current. So that leakage current also we are considering in order to find the total amount of output collector current of your common emitter configuration. So which is equal to beta IB plus of ICEO. So now in order to represent this ICEO in terms of ICBO, it is equal to beta plus 1 times of your ICBO, where ICBO is a common base leakage current. So we can also represent that common emitter leakage current in terms of your common base leakage current. ICEO is equal to beta plus 1 times of ICBO. So now this collector leakage current ICBO is influenced by your temperature variations. So as like in your PN junction diode, so when I am applying a reverse bias, when I am applying a great amount of your reverse bias voltage, the junction temperature increases. When the junction temperature increases, so your covalent bond rupture can takes place. So that direct rupture of your covalent bond can free some charge carriers, and those charge carriers which are free from those covalent bond rupture can again collide with another atom, which can release your again the free charge carrier movement. We have it in your at the output. This cumulative increase in the amount of collector, which will increase the amount of collector current due to your temperature. So current increases, then junction temperature increases. When the junction temperature increases, then amount of collector current also influenced by this charge carriers due to the temperature increase. Hence here the operating points need to be stabilized. So it is necessary to keep your IC constant, though if you are increasing your junction temperature. Next, the individual variation, as I already discussed that. So as the value of beta of the beta and the value of base to emitter junction or not base to emitter junction value for a silicon it is 0.7, 0.6 to 0.7. For a germanium diode it is under 0.2 to 0.3 volts. So though I have taken the same type of semiconducting material, silicon either of your germanium, it does base to emitter junction value as well as your current gain, the DC current gain, same values. So hence we have just given the values of maximum to minimum ranges. It is from 20 to 500 for beta value. Beta maximum to minimum, minimum to maximum range is 20 to 500, and VB value we have mentioned not exactly the value of a 0.6, not exactly the value of 0.7. It might be in the range of your 0.6 to 0.7. So due to that variations also the operating point may change. So if I change the parameters of the transistor, so you are if I replace the transistor, or if I replace here one of the biasing resistor R1 or R2, so R1 all the resistors will have some tolerance plus or minus 5% or plus or minus 10 or plus or minus 20%. So they will have for example 1 plus of 5%. So 1005 ohms will have in some cases. The same resistor, if I am taking 1 kilo with a tolerance of minus 5, then it would be 995 ohms. So due to that, so amount of current flow through that biasing resistors R1 and R2 may vary. So when those vary, R1 and R2, the current flowing through R1 and R2, if it vary, it may affect your base current. When the base current is affected, automatically the collector current is also affected. Hence, the stability will be less. So in order to stabilize, so these all the parameter variation, we require the stabilization method. It is necessary to stabilize your circuit. Next, thermal runaway. As already I mentioned here, IC is equal to alpha E plus. So in a common base configuration, let I am taking a common base configuration. So in a common base configuration, the amount of collector current is equal to alpha IE plus ICBO, because here the emitter terminal is open circuited, hence the leakage current I have mentioned it as a IC. Actually IC is equal to, so now one second. So in a common base configuration, our input terminal is emitter, your output terminal is your collector. So current is, input current is emitter current, and our output current is your collector current. So IC is approximately equal to alpha E. We'll tell that as if I'm neglecting my leakage current, then IC is equal to alpha I, where alpha is the current gain in common base configuration. But if I consider the leakage current, then it would be ICBO, where ICBO is the leakage current when the input terminal is open circuit. So in common base configuration, emitter is my input. So when input terminal is open circuited or it is open, then the collector to base junction, we are making it as a reverse bias. So collector to base junction is a reverse bias. So when it is reverse bias, some amount of current is passing through that reverse bias junction. So that amount of current is treated it as a ICBO. So leakage current. Now as IE, if I replace with the IB plus IC, then it is equal to alpha into IB plus IC plus of ICBO. So alpha IB plus alpha IC plus ICBO. Now IC is equal to, what is IC? Now I am calculating for the total amount of collector current. So I am taking IC as common here. If I am taking IC as common here, then I have here alpha divided by 1 minus alpha into IB plus of 1 divided by 1 minus alpha into ICBO. So as we know that alpha divided by, we have a relation. Shape like alpha, beta, gamma. Alpha, beta is equal to alpha. Beta is equal to 1 minus the configuration. We just have taken this common configuration. Common emitter configuration current again by 1 minus alpha is equal to 1 by 1 minus alpha is nothing but beta plus 1. So if I'm just adding plus 1 to this, then I'll get, so here alpha plus of 1 minus alpha, so plus alpha minus alpha cancelled, then we have 1 by 1 minus alpha, so which is beta plus 1. So hence we replace 1 by 1 minus alpha with beta plus 1, and alpha by alpha minus alpha by 1 minus alpha with beta. Hence our collector current is equal to beta IB plus beta plus 1 times of your ICBO. So now beta plus 1 into ICBO is equal to the ICO, leakage current in emitter, common emitter configuration. So collector current, we are just mentioning that beta plus 1 times of ICBO is equal to common emitter leakage current, which is equal to IC. We replace that with ICEO. So the flow of current and also the the leakage current causes the dissipation of heat. If the operating point is not stabilized, there occurs the cumulative effect which increase the junction heat dissipation. So exactly at the junction, the heat will be dissipated. Again, it can produce the charge carrier generation, and those charge carrier generation can increase the amount of collector current. Again, so that increase in the charge carrier concentration may cumulative effect, due to the cumulative effect, again the junction temperature or the heat will be dissipated at the junction. So Now the self-destruction, due to this, the more amount of heat dissipation, if it dissipated at the junction, so the transistor will be the transistor will be burned out, or the self-destruction of an unstable destruction of an unstabilized transistor is known as the node. We have to, and the destruction of your transistor, we have to stabilize the operating point. So this is the important factors why we have to stabilize, why we have to use the uh, techniques or the biasing methodology, why we have named, why we need the biasing. So is it clear, everybody? Is it clear, Nana? The concept of your stability, what is the need of stability? Is it clear? Yes, ma'am? Do you have any doubts? Please respond. Sometimes my net is in poor condition, so you have that state of voice breaking. Is it clear now? Do you want me to repeat one more time the need of stability or the factors which can affect the need of your stability? Okay, right? I'll move to your next slide. That stability factor. So how many number of stability factors we have it in transistor? That are the things we have to learn now. So at any cost, we have to maintain the collector current in spite of the variations of your leakage current, ICBO, or your IC naught, or in spite of the variation in the current gain, or in spite of the variation in the your beta value or your current gain, as well as if and we have to maintain the amount of current due to the variation in the base to emitter junction variations. So now, so based on the collector current maintained at a constant value in spite of ICBO, or in spite of beta, or in spite of your VBO, VBE. So we have three stability factors which are denoted with. So first one is F, the second one will be your S dash, and the third one will be your S double dash. So these three stability factors are denoted with S letter S. So S is the variation in the leakage current. So we have to maintain the collector current, change in collector current, so must be maintained a constant value with the change in leakage current. So next S dash is the maintaining your collector current if you have a change in the base to emitter junction voltage variation. Next S double dash is the maintain your we have to maintain the amount of change in collector current must be maintained at a constant value in spite of the variation in the current gain of your transistor. So hence here, so when I am just making one must be constant, so IC is constant and I am varying my leakage current. So the other two factors which are here, beta as well as VBE, we have to take here, we have to take these two values must be constant. Whereas when you are calculating your S dash, so stability factor S dash, so we have to take IC naught as well as the amount of leakage current must be constant, as well as we have considered those. So beta is also constant. Now when you are calculating S double dash, when you are analyzing your S double dash, here we have to maintain the values of IC naught as well as your base to emitter junction voltage must be kept constant. VBE is kept constant. Now this is your voltage divider biasing network stability factor SIC naught, which is equal to beta plus 1 times of your 1 plus RB divided by RE, beta plus 1 times of plus RB divided by RE. Now here just if I am taking the ratio of base resistor RB divided by RE, which is far less than your beta plus 1, so then I can ignore the terms RB plus RE in your numerator as well as in the denominator. Then it might be is equal to beta plus 1 into 1 divided by beta plus 1. So beta plus 1 are cancelled. Hence the stability factor due to the variation in the reverse saturation current is equal to 1. So in a voltage divider biasing network, the stability factor is equal to 1. So this is the actual ideal value of stability factor. So if it is greater than 1, then it will be treated as, for example, in a fixed biasing network, if I am calculating dou IC divided by dou IC naught, then so it would be is equal to beta plus 1. So beta plus 1 in a fixed biasing network. If I am taking a fixed bias circuitry in an amplifier, then the stability factor S is equal to beta plus 1. Whereas in voltage divider biasing network, the stability factor is equal to 1. So this is the ideal case of your stability factor. So I could prefer the voltage divider biasing rather than your fixed biasing circuit. The fixed biasing circuit, so which is equal to beta plus 1, where beta is temperature dependent. For example, now if I am taking it as 500, then it would be S is equal to 501. So change in collector current is equal to, so now the amount of change in collector current is equal to 501 times of your reverse saturated current or the leakage current. So it is multiplied by 501 times of your leakage current. Hence it depends on your amount of the variation of your leakage current by a factor of 500 times, 501 times. So hence pore stability is here, the circuit which can provide the pore stability is here fixed bias circuit, whereas in your voltage divider biasing network, so if we are taking this, these are your RB and RE values. So base resistor and RE, base resistor is nothing but R Thevenin base resistance. So if I am taking R1 and R2 as well as the RE value which is far less than your beta plus 1, so the values if I am taking choosing the values of your R Thevenin and RE value which is far less than beta plus 1, then I can maintain the stability which is equal to 1. So S is equal to 1 is a so dou IB divided by dou IC plus beta plus 1 dou IC naught divided by dou IC here. So now this is the reciprocal of your stability factor. So S now I replace with 1 by S, dou IC divided by IC naught divided by dou IC with 1 by S. So now we are finding, as we know that this is equal to 1 by S. So S from this we will find S is equal to beta plus 1 times of your 1 divided by 1 minus beta into dou IB divided by dou IC. So now the stability factor of fixed bias circuit, so which is equal to beta plus 1 times, this is your stability factor of your fixed biasing circuit. So the change in dou IB divided by dou IC almost, so the base current is will vary very with a finite value. Do you have any doubts, Nana? Yes? Are you able to follow me? Are you able to follow? Yes? Please respond, Nana. Yes? Is it clear, Nana? Everybody, I'm asking a question. Please respond. Is it clear, Nana? The concept of stability factor, how to find in fixed bias circuit, in the comparison of your voltage divider biasing with your fixed bias. Why we prefer your self bias circuit? Okay, right. Let I move to the next slide. Yes. Is there any problem? Any problem regarding your slides, the previous slides? Are you not able to follow? Right. Next, I'll move to your next slide. So, stability factor in fixed bias circuit is equal to S is equal to beta plus 1. So, the advantages and the disadvantages. This circuit is simple. So, only one emitter resistor is required to stabilize your current, as well as the biasing conditions are set easily. So, you can fix your biasing values, but the thing is it is having the more stability factor. So it is more variant to your beta changes or the current gain changes. So that stabilization is poor, and as a heat development cannot be stopped in your fixed bias circuit, we are moving to the voltage divider biasing. So now in this voltage divider biasing, so this is the analysis of your voltage divider biasing, how to calculate the stability factor. So this is your stability factor, which is equal to beta plus 1. I have mentioned as RB and RE. Instead of that, we have taken here R naught and RE. So where the R Thevenin is equal to R1 by R2, hence it is equal to, so beta plus 1 into, if I maintain this R naught divided by RE, which is far less than beta plus 1, then stability factor is equal to 1, right? So now the next thing is bias compensation technique. So if we have, for example, now if I am not having the facilities of to provide your self biasing circuit, then so what are the methodologies we have to use, or what are the bias compensation techniques? So you use your self bias technique, and if the temperature increases, if you have a variation in the beta, if you have a variation in the base to emitter junction voltages for every degree centigrade in rising the temperature. So then the additional components we have to use, so which are temperature sensitive devices. So the compensation techniques need the temperature sensitive devices such as your diodes, your transistor, thermistors, as well as your transistors, which can maintain the operating point constant. So first compensation technique is your diode compensation technique. So now in this diode compensation technique, we have two methodologies. So the connection of your diode at your base to emitter junction at your emitter terminal or at the base terminal, you can compensate the changes in the VB variation, base to emitter junction variation, as well as the leakage current variation. We can compensate those variation of your leakage current as well as the variation of your base to emitter junction input voltage. So now here in diode compensation, first the instability due to your VB variation we will discuss. Later that I will move to your the leakage current variation. Now in this one, what I am doing is, so here in addition with the emitter resistor, in earlier voltage divider biasing circuit, we just have taken the emitter resistor at your emitter terminal, that's it. But so to stabilize the variation in the VBE, we have to take a diode which is connected to the cathode at the emitter and anode to the ground, where emitter is of N type, hence we connected the cathode to the emitter terminal and anode is connected to the ground. And so in order to properly bias this transistor forward, always forward, so we used a series resistor. We used a constant amount of voltage, which makes your diode D to forward, and in order to avoid the high amount of voltage state. Now here, how this after connecting this diode, how can it manages your VBE variation? Now, so your transistor is of NPN type. So if I'm taking a silicon or a germanium, the same type of PN junction diode I have to take. So for example, this is a silicon transistor. Now I have to take a diode with the same type of the material, with semiconductor material, silicon. If I am taking your transistor as a germanium transistor, semiconductor material if I am taking it as a germanium, then I have to take the diode is of germanium type. So with that, so amount of base to emitter cut-in voltages and the amount of cut-in voltage of the diode, the amount of reverse voltages of the diode, as well as the amount of reverse voltages which are applied to the base to emitter junctions must be equal. So the junction operating voltages of transistor as well as your diode is maintained constant. So here the diode is forward biased by the source VDD and the resistor, where resistor RD. The variation in VBE with temperature is the same as the variation in the VD with the temperature. Hence, the quantity of, for example, if VBE is increasing, then VD also increases. So we can maintain the amount of change in the variation in the VBE, which is compensated with the diode. So which this reference VBE minus VD will be maintained at a constant value. Hence, if we maintain the amount of voltage difference between base to emitter junction and your diode voltage, then the base current will be maintained at a constant value. So when base current is maintained at a constant value, the operating current IC is also fixed at a constant value. So on the DC load line, it may not shift anywhere to from a center point. So like this we can, so the IC is remains constant in spite of your variation in the VB. So this is the one method of compensating your IC collector current due to the variation in the VB by connecting a diode at the emitter terminal. So when I connected at the diode at the emitter terminal, of same time if I am taking, so the amount of the effective amount of base voltage, now it depends on VBE as well as the amount of voltage across your diode D. So if I have any changes in the base to emitter junction voltage, that can be compensated with your diode voltage VD. So then we can maintain a constant amount of voltage at the base of your transistor. So when we maintain a constant amount of voltage at the base of the transistor, the base current is maintained at a constant value, and the collector current is also will not vary. So it will be fixed with a constant value. Next, we'll move to your diode compensation due to the instability of your reverse saturation current or your leakage current. Now the leakage current IC naught is now I'm just we connected your diode instead of at the emitter, we connected at the base. Okay, we just replaced the R2 with the diode. So for the amount of current flow through this resistance R1 is equal to VCC minus VBE divided by R1. So as the total amount of current, so I is equal to IB plus of, so here the amount of current passing through the diode is equal to 1 second, amount of current passing through the diode is equal to I naught, then total amount of current passing through R1 is equal to IB plus I naught. So where IB is equal to base current is equal to I minus of I naught. So for a germanium transistor, if base to emitter junction is 0.2 volts, which is very small, we can neglect your base to emitter voltage with the temperature. We can write here I, that our total amount of. So if I neglect here amount of base current IB, then I is approximately equal to I naught, where that amount of I is equal to VCC by R1. So when VCC by R1, where VCC is the fixed DC voltage and R1 is a fixed resistor what you connected with the voltage divider network, which is constant. Hence here when I is equal to VCC by R1, so here the collector current is equal to beta IB plus of 1 plus beta IC naught. When I substitute the values of your IB instead of here IB, I minus I naught, this I am replacing this IB with I minus I naught. So beta into I minus of I naught plus of 1 plus beta into IC naught. Then we have here the collector current is equal to beta I minus of beta I naught and minus of 1 plus of beta IC naught. So we have here IC is equal to beta I minus beta I naught. So neglect your reverse saturation leakage current IC naught, then it is plus of beta IC naught. So neglecting your reverse saturation current IC naught, then we have beta IC naught. So I naught is equal to IC naught now. So replace that I naught with IC naught. So if I am replacing with the amount of current, because my diode is reverse bias, so amount of current flowing through that diode is the reverse saturation current. Hence if I am replacing this I naught, diode current I naught with IC naught, then we have here beta IC naught minus beta IC naught plus beta IC naught cancel. Then we have the collector current is equal to beta into I, where that I is equal to VCC by R1. So as I constant, so which is depends only the magnitudes of your DC voltage as well as on the resistance R1. So as I is constant, so IC also remains constant. So we can say that so the change in your leakage current with the temperature are compensated by a diode if I connect at the base. Due to this, the collector current remains constant. So the reverse saturation current I naught of the diode will increase with the temperature at the same rate as the transistor collector saturation current IC naught. So next compensation technique is your thermistor compensation technique. So thermistor is your temperature sensitive device. It has negative temperature coefficient. So when it is having a negative temperature coefficient, the resistance of the thermistor increases with the temperature decrease. The resistance of the thermistor decreases with the temperature increase. So now how to compensate the self biased or your fixed bias circuit, the voltage divider bias circuit with the thermistor compensation. So now let me connect it. So we connected your thermistor across here collector terminal and the other end of your thermistor is connected at the emitter terminal. So the amount of current flow through the thermistor is denoted with the IT, and amount of current flow through your emitter resistor RE is equal to IE plus of IT. So since the amount of current flowing through the RE is now not only with IE, it is also added with your thermistor current IT. Hence IE plus of IT is flowing through your resistor RE. Now here an amplifier circuit, the changes that occur in a leakage current or in base to emitter junction voltage and the beta with temperature increases the collector current. So in order to maintain that collector current, the thermistor is employed in the collector current. When the temperature increases, the resistance RT of the thermistor decreases, which increase the current flow through through the thermistor, because the resistance is decreasing due to your temperature increase. When the resistance decreasing, then the amount of current flow through thermistor is increase, IT increasing. So when IT increases, so the voltage drop across here, emitter resistor is also increasing. Now the voltage developed across the emitter resistor is also increasing. So which reverse biases your emitter junction. So when that base to emitter junction is reverse, actually we need to provide a forward bias voltage, but due to this increase in thermistor current, the emitter voltage is increasing. When that emitter voltage is increasing, base to emitter junction, the net amount of applied base to emitter junction voltage decreases. When that amount of base to emitter junction voltage leads to the base current to reduce. When the base current is reducing, then obviously the collector current is also decreased, or it can be compensated with the same amount of increase in the collector current. So that can be compensated by using your thermistor circuit like this. So we can compensate the amount of collector current due to the or your amount of reverse saturation current or the EBE or beta variation by connecting a thermistor component across your collector to emitter. So is it clear, everybody? Yes. Is it clear, Nana? Is it clear? Let I move to the next slide. Okay, right. Next, we'll move to your next slide, which is your sensor compensation. So now in sensor compensation, so sensor compensation, the sensors are having your positive temperature coefficient. So positive temperature coefficient is nothing but the sensor resistance is increasing with increase in temperature, as well as sensor resistance decreases with decrease in temperature. Now, how to bias using your sensor, or how to compensate using your sensor resistor. So now in your thermistor, we connected from collector to emitter the thermistor, whereas here when you're moving to your sensor compensation, I have to connect the sensor at your collector to base. So now this collector to base junction is connected with your sensor. The amount of current flow through that transistor is coupled as a base current to the transistor. Right now, if temperature increases, the resistance of the parallel combination of above figure will have. So the equal resistance here, the RS in parallel with your R1. Hence here, the resistance R1 increases and their voltage drop also. Thermistor, sorry, 1 second. Actually, sensor R1 is also increases, their voltage drop also increases. So this decrease in the voltage. So now, so we are coupling the amount of voltage. So now you look it out here. So in this circuit, so here we are coupling the amount of voltage across this R2 to the base of your transistor. Now the parallel combination of sensor and your R1 will lead the resistor, which is let I take RS in parallel. So your resistance which is connected at this VCC to the base is equal to R1 in parallel with RS. So if temperature increases, resistance of this resistor increases, hence the amount of parallel resistance become more here. When it is more, the amount of current flow is flowing through this resistance, the parallel combination of R1 RS as I1. So here the amount of current is dropped more in your parallel combination of R1 and RC, then the amount of voltage across this R2 is now decreases. So this decrease in voltage drop across R2 can decrease the voltage, the net amount of base to emitter junction voltage, which leads to decrease in base current, and that decrease in base current can lead to the decrease in collector current. And by this, by employing here transistor at base to collector junction, so we can compensate the rise in the collector current due to your increase in reverse saturation current as well as in the base to interjunction, and beta values due to temperature is controlled. So in this way we could compensate the amount of the collector current rise as well as we will maintain the stability of the circuit. So in your voltage divider biasing circuit. So these are the revision concepts which you wanted to take a review. Now we'll move to your next PPT, which is your frequency response of your CE amplifier. So up to this point, it is okay? Yes, the concept is clear. Need of stability. So why we require the compensation techniques? How many types of stability methods we have to maintain a constant quiescent values and to have your faithful amplification at the output. Without distortion, we will get your output using those compensation techniques. Is it clear, everybody? Yes? Now, we will move to your CE amplifier response. So tell me, Nana, what is your problem? So do you have, you can chat, Nana, tell me. Satya. Is the concept is clear or not? About the stability, compensations. Yes? Now we will move to your next. Concept, which is frequency response of CE amplifier. Okay, right. Now, let us move to your next concept, which is your CE amplifier frequency response. So small signal low frequency transistor amplifier models we have to study it now. So now the transistor acts as an amplifier by raising its strength of the weak signal, and the DC bias voltages are applied at the base to emitter junction and the collector to base junction, which maintains your forward bias condition at the input junction and a reverse bias condition at the output junction. Now, so this is the transistor amplifier, common base amplifier. Now we used VEB, which maintain the base to emitter junction forward. VCB can maintain the collector to base junction reverse. So with that, your transistor is operated under linear or active region. Now by introducing this, you verify this. So now by introducing AC signal at the input of your transistor in a common base configuration, input terminal is emitter. Hence, we connected the AC signal which to be amplified must be applied to the input terminal. Hence, we connected to the emitter. So, the positive terminal is connected. Your AC signal, alternating current signal is the weakest signal strength voltages are applied to the emitter terminal or the input terminal of your common base. So the small input voltages results in a large output voltage due to the DC voltages VEB and VCB. So this makes the amplification. The applied DC voltages will maintain that amount of the greatest amount of the amplification is the causes due to the applied DC voltages VEB and VCB. Next, so now why we call this as a voltage amplifier. So now if I'm applying, if I'm changing your voltage, the AC voltage change with a finite amount of changes, 0.1 volt, I'm applying. So now when I'm applying 0.1 volt of base to emitter junction voltage, so I just change in 0.1, and don't think that only for 0.1 volt your base to emitter junction is forward bias. So if it is silicon, you have to apply 0.6. Now I'm telling the previous value of the input voltage. For example, it is a 0.7 volts. Next voltage what you apply on input is 0.8. So now the change in between the previous and the present value of the applied input is 0.1 volt. With that 0.1 volt of signal, if I am applying at the input, the change in input voltage. So with that magnitude of change in input voltage, if we have a change in the input current, i.e. emitter current is 1 milliamp. So your circuit is under common base amplifier. So in a common base amplifier, the current gain is 1. Hence, approximately the output collector current IC is also equal to 1 milliamp. Now that 1 milliamp, if we pass through a load resistor with a value of 5 kilo ohms, then we have the output voltage across the collector terminal or across the collector resistor RC is equal to 5 kilo ohm into 1 milliamp, will get 5 volt. So 0.1 volt change we are applying at the base to emitter junction. With the smallest change in 0.1 volt will lead to the greatest extent, the greatest amplification at the output of your amplifier with a magnitude of 5 volts. Hence, so your voltages are just the smallest change in the voltage are amplified with the largest magnitude. So these are known as the voltage amplifier. Now, this is the simplest common emitter amplifier circuit. So now we have used a coupling capacitors, we used VBB, we used VCC, and this VCC provides reverse bias, this VBB provides the forward bias, for junction is input junction forward bias. So now we are coupling your which you wanted to amplify. The AC signal is coupled as the VS through a coupling capacitor to the base resistor RB through a base resistor RB. Now the collected output across this load resistor RC is 180 degrees phase shift. We have it since VC is equal to VCC minus of IC RC, as VCC is a fixed voltage. If I am going on increasing my input signal, then IC is increasing, the negative term is VCE leads to negative. So for a positive applied input voltage, you'll have the negative voltages. For the negative applied input voltages, you have due to your negative current. So negative current transfer, you have the positive voltage. So in between, only in a common emitter amplifier, we have 180 degree out of your output is out of phase with your input. So 180 degrees of phase shift is available in your common emitter configuration, whereas in common base and common collector, we doesn't have any phase differences. Phase difference is between your input and output in the common base and common collector. Now, like a DC characteristics, how we have just calculated the input resistance, output resistance, and the current gain as well as your voltage gain. After connecting these all the common your input, so we have to do the AC analysis. So in order to find this input resistance, output resistance as well as the gain and current gain. So in order to apply the AC analysis, so we have to take the frequency response of your circuit. So why I am taking your frequency response of the circuit is because I am applying an alternating current signal with a different frequencies started from the zeroth frequency to the largest frequency. We can apply it with a finite amount of magnitudes at the input, and then we will verify so which frequencies are allowed by that CE amplifier, which frequencies for which frequencies it is having the less gain, for which frequency it is having the constant gain, for which frequency it is having the more gain. And so those all the things we can do it using your AC analysis. Now input resistance, when I wanted to calculate, so then it is equal to change in the base to emitter junction voltage. This is the ratio of change in emitter base to emitter junction voltage with respect to the input current, base current IB. Now next slide, output resistance. If I wanted to calculate in a transistor amplifier, I have to take the ratio of your, by the definition you can take output resistance. So it's the ratio of output voltage to the output current. Output voltage in the common emitter is VCE and output current in common emitter configuration is IC. Hence R naught is equal to change in VCE divided by change in collector current. Now, so in order to find the output voltage across your load resistor, so always in a single stage amplifier, we will treat your collector resistor as a load resistor. But when I am coming to the multi-stage amplifier, so you're you have a resistor which is output resistance. So in order to find that effective load, so in order to find that effective load, we have to take the parallel combination of your collector resistor as well as your output resistance of the amplifier circuit. So now this is your effective collector load. So RC is the resistance which is connected from VCC to the collector terminal RC, but every transistor will have the output resistance, and that output resistance, it depends on the output voltage and output current. Now if I wanted to find the effective load on the collector output terminal, then I have to take the parallel combination of your resistor RC as well as consider your output resistance of the amplifier. So then it is a parallel combination of RC and R naught. So for a single stage amplifier, as R naught is very less in your common emitter amplifier, whereas R naught, the output resistance of common base is high, and the output resistance of your common collector is low. Now the output resistance of common emitter amplifier is also low here. So now RC in parallel with R naught approximately equal to the collector resistor RC. So the effective load resistor of common emitter configuration is approximately equal to the collector resistor, which is RC, since the R naught is very less in your common emitter amplifier. Next, in multi-stage. So if I'm connecting more than one stages, so in order to have a more amplification of voltage magnitude level, so we have to couple one more stage as the second stage, the same type of CE amplifier I'm taking. Now, in a common emitter amplifier or a multi-stage amplifier, so the effective load resistor is calculated by including the input resistance of the second stage. So now this R is the effective load is equal to RC in parallel with R naught in parallel with Ri, where Ri is the input resistance which act like an load to the first stage. Hence, so we have to consider the input resistance of the second stage so as to calculate your effective load. Now, so as I already mentioned, the first stage output resistance is less. So effective load is approximately equal to RC. Now, if I consider the input resistance, then so RC is high as well as your input resistance of common emitter of second stage is also high. Hence, it is RC in the effective load is the parallel combination of RC and as well as the input resistance of the second stage. So, RC in parallel with Ri is equal to Ri divided by RC plus of Ri. Next, current gain of common emitter amplifier as like in your common emitter configuration. It is by definition it is denoted with the beta as it is equal to change in this is change in IC with respect to your change in IB. So in a common emitter amplifier, the input current is your base current. Hence, so change in IC with respect to output current to the input current. So this is how to calculate your beta. Next, voltage gain. So to find the voltage gain, we have to find the the ratio of output voltage to the ratio of output voltage to the input voltage. So output voltage is VCE, whereas input voltage is based to emitter junction voltage. So VCE we can obtain by taking the drop across the effective load. So we have to take the change in output current. So delta IC into of effective load REC, and input voltage can be calculated by taking the product of change in input current, the current which is passing through the input resistance Ri. So the change in input current in your common emitter configuration is delta IB. So delta IB into Ri. So delta IC divided by delta IB can be rewritten as a beta. So beta into RAC divided by Ri. So for a single stage, as already I mentioned here, RAC, the effective load is RC. For a multi-stage, RAC is equal to parallel combination of RC and RI. Is it clear, everybody? Is it clear, Nana? Okay, right? So this is how to calculate here. The parameters in your amplifier. So in the next class, I'll wind up with the H parameters, the session of your revision, as well as we are going to learn about your common emitter single stage amplifier and multi stage amplifier. So tomorrow we'll wind up your unit 2. Okay, thank you, Nana. So today's session, let us stop here.